Hello and welcome to the Open Heat and Mass Transfer course brought to you by a cooperation project between RWTH Aachen University and the University of Twente. This video is the first video with the topic of diffusion, and we will have an introduction to the topic of mass transfer. The learning goals in this video are as follows. First of all, we would like to understand the basic mechanisms and the basic of mass diffusion. Second, we look how diffusion takes place in binary mixtures, and we will learn about the description of the diffusion process by Fick's law. Last but not least, we are again interested in profiles, not the temperature, but the concentration profiles for the special case here of one-dimensional equimolar diffusion in a binary gas mixture at rest. We will learn what this means in a few minutes. But let's first look at diffusion itself. Diffusion is a process that takes place everywhere in nature, everywhere in our body. If we look at the lungs, if we look at the kidney, or even here in the kitchen, if we start making a tea, we will see how the diffusion process is responsible for the tea molecules here to distribute evenly inside the liquid volume. And this is actually already an indicator for a very important characteristic. Similar to temperature, we have a process that leads to an equilibrium and to a more or less homogeneous distribution of the molecules inside the liquid. And how to describe this process coming from this non-equilibrium state to the equilibrium state, that's the thing that we want to tackle in this lecture series, and that's now the basic of diffusion. And of course it has again something to do with resistances, who will take the process of diffusion to last a specific time until the equilibrium is reached. I already talked about the case that diffusion takes place everywhere in our body. Here is an example for a dialysis system. Usually the dialysis, so the blood filtration, takes place in our kidney and liver, but due to circumstances it can happen that the kidneys that do not work as they should work, and in this case engineers have brought it up. We have the chance to mimic the process of blood filtration outside our body, and that's what we call then the dialysis, and there are machines for that. We are also here at the University of Twente working with this topic, so if you're interested you are able to find new ideas and to contribute. But this is very important, that the process of diffusion here is something which is important to describe, to develop those membranes. But not only here in the kidney, but also everywhere else in the body. If you look at on cell level, there is diffusion, the main mechanism. If you look how you're cooling, if you're sweating, then of course there is the liquid on your skin that evaporates. This is also limited by diffusion. So we are always tackling processes of diffusion. Now, let's look at the fundamentals and let's look at binary mixtures. Binary mixtures means that we have a system that composes only of two different components. We talk here about gases, so we have the one gas with the molecules, the red ones, and the other gas, the molecules of the blue species. They are all inside one control volume, and we will assume that this volume is constant. There's a constant number of molecules inside, the pressure is constant, and also the temperature is constant. Now, if we start our process not in equilibrium, but if we start in a sense that we have all the red molecules, all species 1 on the left side, all the molecules of the blue species on the right side, and we have a membrane in between that does not allow for any transfer, then we can have a look on this diffusion process as soon as we remove this membrane. So let's look on one important quantity, and this important quantity is the concentration. If we talk here about concentrations, we always talk about the number of molecules per volume. So this is a concentration definition here, and the number of molecules, because there are so many molecules, we don't not count their actual number, we count their number in terms of moles. So this is just a way how to deal with not such high numbers. So we have a unit here, mole per volume, so per cubic meter. And initially we have a concentration of the red molecules here, which is on the left side high, on the right side there's a zero concentration of the red molecules, and vice versa on the other side. The two curves here are on the same level because we introduced the part that we are looking at a place where we have a constant pressure, and constant pressure also means that the number of molecules on both sides, or the number per volume, is constant. So it's equal on both sides, so the concentration is also equal on both sides. Now let's remove the membrane in between, and what will happen, of course, if we do not force the molecules to move by some kind of ventilation system which we apply to this, but just let this process develop over time, we will see that the red molecules will somehow start to actually move, or we think that they move to the right side, and the blue molecules move to the left side. This is due to the Brownian motion process of the molecules, which move to all directions, and the direction is not that they are actually moving from left to right, the red ones and the blue ones from right to left, but all of those molecules, they have a random movement to any direction. So this molecule can move to the right direction until it hits a wall, and then it will be redirected, and due to molecular interactions they will have specific path lengths, then they move around. And due to this movement, it happens that the concentration on the left side of the red ones decreases in time, and it increases on the right side. And what we also see is that we have gradients taking place here, and that there is a flux, a net flux of molecules, of red molecules, from the left side to the right side, because the concentration increases. And the same happens to the blue molecules, which are initially on the right side. They will eventually move to the left side. This process will take place until a specific point in time, and in the long term they will reach equilibrium. Of course, the process, it's similar to the temperature. It will take mathematically an infinite amount of time to finally reach the equilibrium, but we can say in practical applications that after a long time we have reached this equilibrium, and we see that the concentration, because both volumes were of equal size, is now half here. So the concentration of the red molecules plus the concentration of the blue molecules is again our total concentration, and both concentrations on both sides of the compartment are equal. Now let's look a little bit on the statistical or molecular approach how to describe this diffusion process. Just now let's focus on the left side where we have a non-equilibrium state. Then of course, if those molecules move, they move either to the right side or to the left side. So their movement is statistically the same number of molecules moves to the right side as to the left side. But if we take this here, for instance, as a control plane and the initial state, then we see there is a chance that red molecules move to the right side. But because on the right side there are no red molecules, or there are only a few red molecules, the probability that red molecules now move from the right side to the left side is much lower, or as in this image, 0. And due to that the probability of movement from the left to the right is higher than from the right to the left, we have actually a net flux of molecules from left to right. So again, from the concept, because this is a very important thing to memorize, is that the probability of the red molecules crossing this control plane from the left to the right depends on the number of molecules being on the left side and on the right side. So the probability that a red molecule crosses the control plane from left to right is very high because there are a lot of molecules on the left side, but vice versa, there's not a high probability from the red molecules that are rarely present here to move from the right to the left. And because of that, we have an effective flow of red molecules from left to right. Now, in the equilibrium state, there is a similar or same number of red molecules moving from the left side to the right side as red molecules moving from the right side to the left side. So actually the same kind of movement is still taking place. The red molecules are still traveling and the blue molecules are also still traveling. But from the outer perspective, looking at the concentrations and the mean number of molecules on the left and the right side, we do not see an effective flow of red or blue molecules happening anymore. And this is like a molecular or a statistic concept of this diffusion process. Now, how can we describe diffusion in general? So we can mimic the knowledge, or we can transfer the knowledge from the temperature and heat flux to the concentration and mass flux. And now let's focus on a molar flux, which means that it's a quantity of molecules moving. We do not put this into mass flux, so actually the mass of the molecules that move, just stick on the numbers of the molecules. So the molar flux is again depending on a gradient of the molar concentration. That's what we have seen from the statistical reason, that if we have on the one side more molecules and the other side, there is a net transfer of the molecules. And as we had it also in heat transfer, we have a negative sign for that. Again, it's like from the potential, the sphere or the ball is always rolling down the hill, so there is a negative gradient that plays an important role. And then we have empirical constant that connects the negative gradient of molar concentration with the molar flux. And this empirical coefficient is here the diffusion coefficient, very similar to the thermal conductivity in heat transfer. And then we already come to the description, the mathematical description, and this is called Fick's law. It's very similar to Fourier's law in heat transfer. So the number density, the molar flux here, is equal to a diffusion coefficient times the negative gradient of concentration over a specific distance dx. Important to notice that we have here the diffusion coefficient, which we call the diffusion coefficient 1, 2, meaning that is the diffusion coefficient of the component 1 through the component 2. Vice versa, we have for the molar flux of the species 2 the relation of the diffusion coefficient 2, 1 times the negative gradient of the concentration 2. Again, this diffusion coefficient d21 means it's a diffusion of component 2 through component 1. Looking at the units, we see the molar flux is the number of molecules moving through a plane or through an area in a specific time, so mole per second square meter. That comes from a concentration gradient. The concentration was mole per cubic meter, and then we have the derivative with respect to a spatial coordinate, so we have another meter here. To bring these two together, we have the unit of the diffusion coefficient, and we see that the unit of diffusion coefficient is square meter per second. Now you might say, wow, stop, I know this quantity, meter square per second. This is also the thermal diffusivity. And that's a nice part here. We see that the diffusivity of the molar flux, the D12 or D21, is actually from the unit itself the same as the thermal diffusivity. And also later on we will notice that it's also the same to the momentum diffusivity, which is then the diffusivity of momentum through a boundary layer, and we will compare this in the next videos. So, as I mentioned before, this is very similar to what we have already learned in Fourier's law. Now I would like to come to a connection between the diffusion coefficient 1, 2 and the diffusion coefficient 2, 1. And that brings me again back to what we have called here. It's an equimolar diffusion process in a binary mixture. And for that, let's look at some mathematical parts. So first of all, the concentration of component 1 plus the concentration of component 2 is a total concentration. And the total concentration, C, is constant because we have the assumption of constant pressure and constant temperature. We can take the derivative of that. So if we say that the derivative dx1 dx plus the concentration of 2 with respect to the spatial coordinate dx, then because it's constant, the derivative of a constant is 0. So we come up with this equation. And the next part is that we can say that the flow of component 1 plus the numbers of component 2 is also equal to the total number, and this is then again constant. So because of that, we can also say that the flux of the component 1 plus the flux of the component 2 is also, the sum is also equal to 0, which then means that the flux of component 1 is equal to the negative flux of component 2. This just translates that if a red molecule moves from the left side to the right side, there needs to be a blue molecule moving in the other direction in order to maintain a constant number of molecules in each plane, which is important to remain a constant pressure in every plane and not to get pressure gradients. Now we can combine this utilizing Fick's law. So what we have is, because both of them are 0, we can just add them together, and what we come up with is that this equation here is only valid if the diffusion coefficient 1, 2, so the diffusion of component 1 in component 2, is equal to the diffusion of component 2 in 1. So we can omit these indices, and we can say for binary mixtures and equimolecular diffusion process, we have a diffusion coefficient D. Let's again look on a molecular statistical level on that process. So the mechanical equilibrium, which we require, is meaning that the pressure is area constant, which translates to a substance concentration to be identical everywhere in the system. Now we can again have a control volume and see what happens if molecules move. So let's assume that molecules move over those boundaries, and a red molecule now moves to the right side. Two things can happen. It's important to maintain the number of molecules inside this control volume to be constant. So first of all, if the red molecule moves to the right side, another red molecule can move from the right side to the left side. If this happens, we will have on a macroscopic level no visible change. This could be happening if we are in an equilibrium process where the process of the chance that red molecules move from the right side to the left side is equal to the movement of red molecules from the left side to the right side. The other thing that can happen is that a blue molecule replaces the molecule A. And in this case, we see a visible change. But because we have a direct exchange between a red and the blue molecule, it has to be from the macroscopic view an equal diffusion process from the red ones into the blue ones compared to the blue ones into the red molecules. And this is the meaning that the diffusion coefficient of both is equal. Now, we have always talked about number flows or flows of molar fluxes. Now we are interested and we would like to know what is the mass flux, because what we can measure much easier in daily life are masses instead of just numbers of molecules. So we know the Fick's law, in which states that we have a number molecular flux of n dot double dash of the component I, which is equal to the diffusion coefficient times the negative gradient of concentration. If we want to come from a number flux to a mass flux, we have to multiply first both sides with the molecular mass. So the molecular mass times the number will lead to here a mass flux, and on the other side we can state that the multiplication of the molecular mass times the concentration will lead to a density, and as such we can come up with an equation that relates the mass flux to a negative diffusion coefficient, which is still the same, times concentration or a gradient in mass, and here it is the rho I, which means it is the density of component I. If we want to express this in a density of the mixture, then we have here rho as the density of the mixture, and we need now to introduce a mass fraction. That's a component Xi. We will talk about this in the next video a bit more, how those quantities are related, but this is the fraction of mass times the density, which will then eventually be the partial density rho I. Now, instead of mass flux m dot double dash, we will use here in these videos and in these lectures another letter to cope with that, and that's the letter J. And we use this because we want to define later on a mass flux that results not only from diffusion but also from advective processes, and we want to separate this from diffusive processes, and so we will describe the mass flux that just results purely from diffusion by the letter J. Now, that was the first lecture in mass transfer. The comprehension questions that we have for you are, of course, it starts with what is the meaning of Fick's law, and to explain Fick's law we can directly translate this to heat transfer. We can say, okay, Fick's law is something that describes the process of diffusion of mass similar to Fourier's law, and it relates the molar flux of a component towards its gradient, so its spatial change of concentration, and the connecting variable is the diffusivity d. What does equimolar diffusion mean? In an equimolar diffusion we have two components, and the one component diffuses into the other one, and vice versa, the other component diffuses into the first one, which then leads to a diffusion coefficient of d12, being equal to the diffusion coefficient of D21. The third part is what is the relationship between molar flux and diffusive mass flux. We have seen that if we start with the description of molar fluxes, we can multiply this with the molecular mass, and then we come up with a mass flux, and we can replace the concentration, which is the number density of molecules per volume, by the density of the component, or we can then replace the density of the component by the mass fraction times the density of the mixture. And with that, I would like to thank you for your attention and see you in the next video.